Then last session we started with naive Bayes. It's another way of doing classification. But then for that we needed the Bayes theorem. And I noticed that most of you didn't know, or it's your first time seeing Bayes rule and Bayes theorem. So I'm going to give you an intuitive example of what Bayes theorem is about. Okay, so this is the formula for Bayes theorem. So whenever somebody tells you write down Bayes rule, this is Bayes rule. The probability of event A given event B is equal to the probability of event B given A times probability of A divided by P of B. And these terms have their own names. So just memorize this formula, okay? So there is nothing about it. So we have to memorize it. This is likelihood. This is prior. This is evidence. This is posterior. So likelihood, prior, evidence, posterior. But Bayes' theorem is nothing but this observation. The joint distribution of two events, A and B, it means that these two events are occurring at the same time, is just the probability of A given B times probability of B. So it's the same formula here, we are just replacing A and B. We're just switching the roles of A and B. So it's the same thing. But then we know that P of AB is exactly P of AB. By definition, it's just a trivial thing. This is the same thing. It means that this term, if the left-hand sides are equal, the right-hand sides of these two should be equal. And that's just the Bayes rule. So you keep P of A given B, this is equal to this term divided by P of B. So that's your Bayes rule. So there is nothing complicated about it. It's P of A given B times P of B is equal to P of B given A times P of A. So it's just a reformulation of your joint distribution. So everything is exact mathematics. So, and Bayes' rule has been around forever. So there is nothing complicated about this. The science is known, but let's see an example. Why do we use Bayes' rule in practice? Why is it important? Sometimes you're interested in P of A given B, but then you cannot compute it in a direct fashion. So you have to compute it in an indirect fashion. By indirect, I mean you have to use the Bayes rule. Why? Because P of B given A is easier to compute, P of A is easier to compute, and then P of B is also either a constant, you can ignore it, it's not going to affect your optimization, so you can just ignore it, or it's easy to compute. Sometimes this is hard to compute in a straightforward manner, but then it's easier to compute it through Bayes rule. Let's see an example of this case. So we are in COVID era, and then there are some tests for COVID to see whether somebody is positive or negative, okay? So let's say there is a test, a particular test, and its job is to tell us whether somebody is COVID positive or COVID negative. That's the job of the test. Maybe these nasal swabs. And let's say they are 90% sensitive. What does it mean to be sensitive? It means that this is the definition of being sensitive. It means that the true positive rate is 90%. So what is the true positive? Out of the ones who are actually positive, our algorithm is 90% correct. 90% of the time correct. So that's the true positive rate. So in other words, it's leading to 90% true positive results. So what is a true positive result? Correct identification of COVID. So a patient comes in, that patient has COVID, our test is going to be 90% accurate. So 90% of the time it's going to say yes, this infected patient is positive, and then 10% of the time it's making a mistake. Okay, no test is perfect, so it's going to make a mistake. So far so good. And what is this term? How is it related to Bayes' theorem? This term corresponds to your likelihood. Given that I know that somebody is infected, our algorithm, our test is 90% accurate. So that's this probability. Okay, and that we know because we know our test and we know how accurate that is. We know what is how sensitive your test is. Okay, that's something we know. What else do we know? We also know that our test is 80% specific. What does it mean? It means that its true negative rate is 80%. What does it mean? A COVID negative patient comes in And then our algorithm, our test is going to be 80% correct, 80% of the time. And 20% of the time, it's going to mistake a non-infected person by an infected person. So a non-infected person comes in, and there is 20% chance that the test is going to identify this non-infected person as COVID positive. So it's making mistakes 20% of the time. So there are two types of mistakes that a test can commit. The first one is the false positive rate, and the other one is the false negative. So the false negative rate is 10%, and the false positive rate is 20%. Okay, so far so good. Why do we need this term? This term is going to appear in your evidence later on. And then what is our prior? So we are going to assume 5% prevalence. What is prevalence? It means that 5% of people are infected in the society. So if you watch TV these days, there is this number that are being reported each day that this many people got COVID. We know the total population of the US. We know that this many people are infected. You find a ratio, and let's say that's 5% of the population. And where is this term coming in? That's your prior. Okay, 5% of your population is infected. Okay, so far so good. But who cares about these numbers? These numbers we know. We know how sensitive our test is, we know how specific it is, and we know that 5% of the population is infected. So all of these we know. But what are we interested about? We go and take a test because maybe we have some symptoms or we don't. We go and take a test, and we want to know if our result comes out positive. Do we really have COVID, or it's just a flu? Okay, we go and take a test. Our test comes in positive, and then we want to know, are we truly infected? And that's the posterior. We know that our test is positive, conditioned on our test coming out positive. Are we really infected? So that's the thing that we are interested in. Probability of being infected given that our test came out positive. So that's P of infected given positive. And this is hard to compute without Bayes rule. But Bayes rule is going to make our life much simpler. We know this term, P of positive given infected. That's the true positive rate of the test. P of infected is this 5% of the population, and P of positive, you can just break it apart. You can say P of positive, if P of positive given infected times P of infected plus P of positive given not infected, P of not infected. So as a person, we are either not infected or infected. So there are only two cases. That's the probability for the first case, the probability for the second case, and then you are just multiplying these terms together and add them up. That's going to give you the probability of positiveness, and that's your evidence. And this is exactly the false positive rate comes in. So that's why we needed the second information. Okay. So now let's just plug in the numbers. Our test is 90% sensitive. So that's this number. We are just copying and pasting the true positive rate. We are putting it here. 5% of the population is infected. This term is exactly the term above, and then some additional terms. This probability of being positive given not infected is the false positive rate, that is 20%. And then this number is 1 minus the population that are infected. So it's all the rest of the population. And that term we also know, it's 1 minus this term. So if your test comes in positive, there is 90% chance that you're infected, given this information. And this is exactly what we're interested in. So is Bayes rule clear? Do you have any questions? Okay, perfect.